Welcome back to Math 104. We begin video set number 8. Let's recall the example in which you toss a pair of fair dice, one red and one blue. Consider again the following events. F, that the red die shows a 2, H, that the sum of the two dice equals 7, and I, that the red die shows a 5. For convenience, here is our listing of the full sample space of this experiment. The dice are fair, so these 36 outcomes are equally likely. Let's investigate what the notions of independent events and mutually exclusive events have to do with one another. This is a common source of confusion, so it's worth making a point of really understanding this. Are H and F independent of one another? This we have done already, but let's recall how it goes. The probability of H given F turns out to be 1/6 if it's known that F has already occurred, if it's known that the red die shows a 2. Then how many of these 6 outcomes have a sum equal to 7? One of them does. 1 out of 6 is the probability of H given F. Since the probability of H is also 1/6, it is 6 out of 36. All 6 outcomes along this diagonal line here are in the event that the sum equals 7. So 6 out of 36, or 1 out of 6, is the probability of H. That means that these probabilities, the before probability and the after probability, are equal to one another. The answer here is yes. Knowing that F has occurred has no impact on how likely we think it is that H will occur. Are H and F mutually exclusive? No, they are not mutually exclusive, because they can both occur, and the outcome 2 on the red, 5 on the blue, is the outcome that they have in common. So the answer here is no. Events can be independent, but not mutually exclusive. Now let's look at how I and F are related to one another. I, the event that the red die shows a 5, and F, the event that the red die shows a 2. Are I and F mutually exclusive? Yes. They are mutually exclusive since they cannot both occur. There is no outcome in common between them. Are I and F independent of one another? The probability of I given F equals 0. If it is known that F has occurred, there's no chance for I to occur. If the red die already shows a 2, it cannot turn out that it will actually show a 5. On that roll, it shows a 2 and that's it. So the probability of I given F equals 0, and that is certainly not equal to the probability of I without knowing anything about F. That is certainly not equal to the probability of I itself before any information is known about F. That probability is 1/6. The conclusion then is that I and F are not independent of one another, and this makes sense. For two events to be independent of one another, that would mean that knowing that one of them had occurred would give you no information about whether the other was going to occur or not. But if you know that F has occurred, that gives you a great deal of information about whether I will occur. It guarantees that I won't occur, that I cannot occur. If I and F are mutually exclusive, then they are not independent of one another. In fact, they are as far as possible from being independent of one another. The occurrence of one dictates the impossibility of the other. The conclusion, and this is important, mutually exclusive is a different notion from independent. They are different ideas. I caution you that it is very common to mix these two notions up. Please go on to the next video where we'll start a new kind of example.